Okay, hello class. We are working our way through chapter 9.3. I'm going to go through these rather quickly. We have already talked about the right triangle similarity theorem. That was when we cut apart the cards, the index cards, and we talked about how we get the three similar triangles. So a couple pictures of that. And if you remember, we could use proportions to find missing lengths, and we kind of went through this idea of using the chart, which at the time was helpful, but today we're going to explore a couple other options. And we are going to be using something called the geometric means. So this is the new part, and my first question for us is, can we find the mean of 18 and 26? So hopefully you're familiar with finding a mean. It's the arithmetic mean or the average. What you guys do, and you've been doing this for a long time, probably since elementary school, is you add the two numbers together and you divide by 2. So that would give us 44 divided by 2, which is 22. And that's what you and I usually refer to the mean. But that's technically what they call the arithmetic mean. There are also geometric means, and if we kind of take a look at this pattern, 3, 6, 12, 24, and I might say, well, what's going on there? And I hope that you see each time you're multiplying by 2. And if we take these numbers and we write them as a ratio, 6 over 3, that's equal to 12 over 6 and 24 over 12. And this is what we call, if you take a look at the way I'm setting up this proportion here, kind of taking, I did this one, the second two fractions. And I said, well, what if I had the number over 6 and compared it to the next number over the 24 over 12 and set up a proportion? When I cross multiplied to solve this, I would get x squared equals 6 times 24. And that's talking about finding what we call the geometric mean. So x would be the square root of 6 times 24, and I'm just going to go through this. We could multiply that out, but what I'm going to do is I'm going to express it as 2 times 3, that's my 6, times 3 times 8, and I'm looking for perfect squares in there, so it's 2 times 3, which is the 6, times 3 times 8, which is 4 times 2, and I'm looking at all the things that can come out. The 3's can come out, the 4 can come out, and the 2 can come out. So really I end up getting 3 times 2 times 2, which gets me back to 12, which was the missing piece here to make that ratio equal. This is called the geometric mean. So the geometric mean of two positive numbers is the positive number x that satisfies this proportion. A over x equals x over b. So when you work that out, you'd find out that x squared, which is what we're looking for, is equal to a times b. And to solve for that, we would take the square root. So x is equal to the square root of a times b, which is our geometric mean. We'll be using the geometric mean, and we're going to do that right now. So if we were asked to find the geometric mean between 24 and 48, the setup for the proportion is going to look like x over 24 equals 48 over x. So it's that missing piece there. And you can solve that, but if you use the geometric mean theorem, it says really when you cross multiply, you get x squared equals 24 times 48, which is what the geometric mean theorem says. So if we're going to look for what x is, we take the square root of both sides. And I just split 48 into 24 and 2 and was able to pull out a radical jail, the 24 square root of 2. This is the geometric mean. As you can see, we're using a lot of radicals in here. I would like you to try to find the geometric mean of these two numbers. Please stop the video Give it a try and bring your answer into class tomorrow. Okay, now that you've done that problem, hopefully you stopped the video and gave it a try. Now we're going to talk about how we can use the geometric mean to solve triangle problems. So you want to get these two theorems copied down. The geometric mean altitude theorem. And it says in a right triangle, the altitude from the right angle to the hypotenuse divides it into two segments. Takes the hypotenuse into this segment and this segment. And the length of the altitude is equal to the geometric mean of the lengths of the two segments of the hypotenuse. So they have called this CD squared, so I'm going to just use an x. So if I was going to find the geometric mean, x squared is equal to, we call this piece y, z. So what we're going to do in this example, we're going to use and apply the geometric mean altitude theorem. So you can see here we have a picture, we have a right triangle, and we have the altitude, which they called x, and our job is to find x. What we did when we were working in chapter 8 was we would say, okay, I've got the two triangles, I've got the small and the medium triangle, small and medium triangles. And if I decide how I'm going to set up my proportion, I'll take the medium side of the small triangle, which is the x, and compare it to the short side, which is the 3. And then I'll compare that to the medium triangle, and I'm going to compare the medium side, which is the 6, to the short side, which is x. So again, this altitude is playing two roles in these two different triangles. And if I was to solve it, we would cross multiply and get x squared equals 18, and we could take the square root of both sides. Now, here's the cool thing about the geometric means theorem. The geometric means theorem allows us to get right to x squared equals 6 times 3, or 3 times 6, right away. So we no longer have to think about those proportions and setting things up. The geometric means altitude theorem says, okay, so if you want to know the altitude, which is our x, it's simply x squared equal to the two little parts of the bottom of the triangle, or how we split the hypotenuse, 3 times 6. Now, of course, I need to solve that. I'm going to take the square root of both sides, and that's the square root of 18. Which is 9 times 2. We're always looking for those perfect squares. And if I take the 9 out of radical jail, I get 3 radical 2. So this geometric means altitude theorem is going to allow us to find missing pieces of triangles without having to go crazy setting up those proportions. If we go back, there is also the geometric mean leg theorem. So if we are looking for a leg like CD, there's a way that we can find that leg without going crazy setting up proportions. So again, it says in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. Okay? The length of each leg of the right triangle is equal to the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Wow, that sounds like a lot of information. But what that means is if we have CB squared, I'm just going to call this piece x, what I'm looking for, if the geometric mean, is I am going to take that, and that's going to be equal to dB, which is the piece that is adjacent to that leg, the closest piece, times the length of the entire hypotenuse. kind of would look like this if I would draw it out separate. It would look like this. Right? So we have the side leg over the short piece of the hypotenuse, and again, that leg over the entire hypotenuse. It will work the same if we're trying to do the other side. So if we're looking for AC, so if I square AC, that is going to be equal to AD, which is that piece that's adjacent, times the entire hypotenuse. So at this point in the video, I just want to make sure that you have these theorems written down. Tomorrow in class, we'll spend time applying them, and I think you'll find that they're really cool and they're really much easier than trying to look at similar triangles and say, well, is that the long piece or the short piece? Is it the hypotenuse? This will allow us to find missing pieces very quickly. Please bring a complete set of notes to your next class, and I'll see you then.